Hello and welcome to Chapter 9.2 in Stevens' Introduction to Statistics, the Think and Do book. So in this test we're going to do a hypothesis test for two means from independent data, which sounds very much like the last section but is actually quite different. So I'm going to put us into full screen mode here. Hypothesis for two means independent data. All right. Here we'll be considering the difference in means between two populations. Now this is different from the previous section in a few ways. So if we look at the last section, what we did, the data came in pairs, right? And we were testing a claim about a mean difference. So we got all the pairs, got all the differences, and then tested a claim about the mean difference, right? In this section, independent data, the data is not paired. We are testing a claim about a difference in the mean. And that's different than the mean difference, right? We're getting the means from two independent populations and testing for a difference in those means. And in the last section, the sample sizes were basically the same. There's the before and after type of scenario. But the sample sizes do not need to be the same. The calculations are much more complicated, and software is recommended. And we'll look at this demonstration to see the subtle difference here. So here we look at the same numbers from Chapter 9.1, only now we're going to consider them to be slightly different. Instead of being the before and after for 10 different men, we're going to have 20 different men, 10 that took no drug. Right? Those are the cholesterol levels for 10 men who did not take the drug. And then this second row will be considered the cholesterol levels for 10 men who did take the drug. Right? It is no longer a before and after situation. Right? And the idea is that the makers of this drug want to claim that their medication lowers cholesterol. So these are all cholesterol levels. Right? And notice I did not put in a difference. In the last chapter we put in a row for differences, and then we just worked with the differences. That is no longer here. We're actually going to look at the means and compare these. Right? But, a couple of things are obvious from here. Right? Clearly the mean from the sample that did not take the drug, 263.2, is certainly greater than the mean from the men who did take the drug, 231.2. So that's pretty good evidence for our drug company here. But we want to know if this is sufficient evidence to support the claim that the difference in means for all men is greater than 0. Right? The data is not paired. We're not looking at differences before and after. We're actually looking at the difference in means between the two groups. And again, that difference in means is over 30. So we might want to strengthen our claim and say the difference in means for all men is greater than 20. We could go for 30, but I don't think we're going to get it because the difference is so close to 30 anyway. So that would strengthen our claim, make our drug sound a little better. And we're going to calculate a test statistic, a t-value, so we're using the t-table again, and decide whether or not we have sufficient data to support our claims. Ideal requirements, simple random samples, and we either need both sample sizes to be greater than 30, right? Because now we have two different samples, so we need them both to be 30, or both populations are known to be normally distributed, right? Or you could actually have both of these, right? You need at least one of these things to be true. And for presentation purposes, I'll be showing you small samples, so we will be assuming that both populations are normally distributed, even if we're not completely certain of that fact. Okay, so notation and form. This is where things get a little ugly, especially if you're not using software. And I will tell you that I will give you a lot of this information. Specifically, I'll give you the degrees of freedom. But let's take a look at our test statistic. It's right here. All right. So we're going to look at our test statistic. X1 bar will be the mean from sample 1. X2 bar is the mean from sample 2. Delta will be the difference in means presumed in the null hypothesis. And then we have a couple of other variables, the square root of a plus b, right? Where a is the variance of the first sample divided by n1, and b is the variance of the second sample divided by n2. And by the way, n1 is the sample size for the first sample, and n2 is the size of the second sample. And s1 squared, s2 squared, those are just the variances, right? S is standard deviation, and if you square it, s squared, you get variance, right? And you can either do that by squaring the standard deviation, or a lot of times you'll just be given the actual variance, right? And the degrees of freedom, because this is a t-value, keep in mind I now need a degrees of freedom. And this is where this particular type of problem gets very complicated. So the degrees of freedom is calculated with this very complicated fraction, right? And what I want to point out now is that in this text, it will be calculated for you. If you use software, it will generally print it out and tell you what the degrees of freedom are. And some texts use a degree of freedom system that's much simpler, and basically you just use the smaller of n minus 1, n1 minus 1, or n2. Right? And that's fine, but what that does is it will generally bring your degrees of freedom lower than it has to be. So we'll use the more complicated formula, which is a little more accurate, but I will be giving it to you in all of the examples and in the summary worksheet and in the problem set. And that's whether you do it in the book or online. Okay, so the degrees of freedom, very messy, but it will be given to you. Critical values of t denoted t sub alpha with a one-tailed test, left or right, and plus or minus t sub alpha over 2 for a two-tailed test, because there's 2 critical values in a two-tailed test and 2 rejection regions. The process, once you get through all the labor, that is the labor in calculating the test statistic, is just like any other t-test from 8.3 or 9.1. Right? That's 8.3 or 9.1. And it's actually the same as any hypothesis test. We start off, we have to determine the null and alternative hypotheses, and that really starts by getting your claim in mathematical notation. And once you get that claim figured out, you'll have something like, mu1 minus mu2 is greater than, less than, equal to, not equal to some presumed value, right? And the null hypothesis will look just like that, only it has the equal sign, right? And delta is some presumed value that comes from the claim. And just as in other hypothesis tests, we have an alternate hypothesis that looks like a greater than sign, or less than, or not equal to, right? And the choice depends on the claim and on the null hypothesis. So notice all this stuff is looking at the difference. It's making a claim about the difference in population means. Last section we were looking at the mean of differences. Here we're looking at the difference of population means. So it's a different problem. And we will first calculate the test statistic using 9.2, and then the degrees of freedom using 9.3 on the previous page. And again, I will be giving you the degrees of freedom. So 9.2 is really what we have to worry about. And then just like any other t-test, we determine whether or not we reject or fail to reject the null hypothesis. We will be focusing on the critical value method, where we get our critical values from table 3, the t-table, right? T-table. Once we get the critical values, we'll get our rejection regions, and you reject the null hypothesis if the test statistic lies in the rejection region. If you have software, we can calculate the p-value. That won't be the focus of of this here because I'm assuming that you don't have software readily available. But if you do have software, you can get a p-value pretty quickly, and then you reject the null hypothesis if the p-value is smaller than alpha, where alpha, again, is the significance level. Right, 0.10, 0.05, 0.01, usually one of those three. Then, as always, we're going to finish off by making an understandable conclusion about the claim. Okay. Oh. So let's look at our example. All right, we have our data. 10 men with high cholesterol that took no drug, 10 men with high cholesterol that did not take the drug. And by the way, if you were doing a true clinical trial, you would probably do the paired data as opposed to this. There's a little too much freedom in this type of problem. But let's assume that we didn't. We have 10 men with high cholesterol that didn't take the drug and 10 different men with high cholesterol that did take the drug. All right? And we want to test the claim that the mean cholesterol level for all men who use the drug is less than the mean for those who do not use the drug. We will assume both populations are normally distributed because our sample size is kind of small here, and we will conduct this test at the 0.05 significance level. Okay, so we are basically claiming, right, that the drug group is lower than the no drug group. So we're saying that mu2, the mean for all drug users, is less than mu1. Another way of writing that is that mu1 is greater than mu2. We're saying that the no drug group has a higher mean than the drug group. But I got to get this with a 0 on one side or the other. Right? So what I do now is I take this equation, I subtract u2 from both sides. So what I'm saying is mu1 minus mu2 is greater than 0. Right? Right? And that's basically what I'm saying, is that this thing is significantly bigger than that thing. Right? If I subtract the mean for all men who did not take the drug and subtract from that the mean from all men who took the drug, it would be greater than 0. Okay. So my claim looks like mu1 minus mu2 is greater than 0. My null gets the equal to sign. My alternate gets the claim because it can without being the same as the null. Now I'm going to calculate the test statistic and the degrees of freedom. Again, I'll calculate the degrees of freedom here, but on example problems in the worksheet or in the problem set, you'll be given the degrees of freedom. So some preliminary values. If you look for the test statistic way down here, it has this A and this B in there. And A is the variance of the first sample over the size of the first sample. So that comes from here. That's the variance of the first sample divided by the size of the first sample. So that's 10. 811.1 divided by 10. And if you do that and round to 2 decimal places, you get 81.11. Likewise, B is the variance of the second sample, right? Over, and now divided by the size of the second sample, which again is 10. And so when you round that to 2 decimal places, you get 86.40. Now to get to calculate the degrees of freedom, let's go over it briefly. I mean, you got to plug in a lot of values, all these A's and B's, and -1 down here, and 2 -1 down there. And if you do this and you do it all correctly, and it's not easy to do it all with a calculator, you get 17.98, which rounds to 18 degrees of freedom. Right. So in homework problems and the worksheet, you'll be given DF equals 18. Okay, so the test statistic, I have to get my sample mean from the first sample, which is 263.2. The sample mean from the second sample, which is 231.2. I take that difference and I subtract 0, because that's delta, which is in the null hypothesis. This right here is delta. Sometimes if we're looking to maybe test a claim where the difference is greater than, say, 20, we'll have a 20 in there. But for this case, it's just a 0. Then we have to divide by the square root of A, which came from here, 81.11, plus B, which came from here, 86.40. So there's our test statistic. It took a little while to get there, but it's 2.473. So let's look for the critical value for this test. I'm testing at the 0.05 significance level. It is a one-tailed test, and there are 18 degrees of freedom. So it's one tail, 0.05, 18 degrees of freedom. So it's a one-tailed test, 0.05, so I'm in this column, 18 degrees of freedom. So there's my degrees of freedom. And I get 1.734. Right, so that's my critical value. 1.734. Right there. Right. And again, I didn't draw the distribution, but if you did, it's a t distribution, so there's a t there. And the critical value is 1.734, and so the rejection region is everything to the right of there. And if you look at your test statistic, 2.473, it is indeed in the rejection region, so we reject the null hypothesis. If you have software, you get a p-value of 0.0118, which is smaller than alpha. That's the significance level, which is 0.05. Right. If you use software on rounded values, you get a p-value slightly different, but still smaller than alpha. So that's good. We reject the null hypothesis. That allows us to support our claim. And specifically at the 0.05 significance level, the data supports the claim that the mean cholesterol level for all men who use the drug is less than the mean for those who do not use the drug. So the your turn problem is just a simple variation. If I had changed my significance level from 0.05 to 0.01, would I still be able to support the claim? And the short answer is no, but here's why. If you look at the critical value at the 0.01 significance level, we'll go to our table here. At the 0.01 significance level, one tail, 0.01, I'm now in this column, 18 degrees of freedom. My critical value is now 2.552. Right? And so 2.552, that's my new critical value. And our test statistic doesn't change. It's still 2.473. And it's a close call, but if you draw a t-distribution here, we have 2.552 is the critical value, and our rejection region is everything to the right. The test statistic is right up above us here. It's 2.473. 2.473. And if you notice, the test statistic is just over here. It is not in the rejection region. So the test statistic is not in the rejection region. And also, by the way, the p-value doesn't change, but now that's larger than alpha because alpha now suddenly equals 0.01. I've changed the significance level. So you would fail to reject the null hypothesis, and we would not be able to support our claim. We would come up with there is not enough sample data, there is insufficient sample data to support the claim that the mean cholesterol level for men who use the drug is less than the mean for those who do not use the drug. So again, the significance level can alter your conclusion dramatically. Alright, so that's too bad, because we were able to do that with the paired data at the 0.01 significance level pretty easily. So if we go to this value, so if you look at the difference in means, 263.2 and 231.2, the difference in means is over 30. And we were able to support at the 0.05 significance level that the mean for all men was going to be, the difference in means for all men was going to be greater than 0. Can we get greater than 5? Right? We want to strengthen our claim. Test the claim that the mean cholesterol level for all men who use the drug is more than 5 milligrams per deciliter lower than those who do not use the drug. Use a 0.05 significance level. Right. So most of all of this remains exactly the same, except now I'm saying I claim that mu2, right, that's the second row, is below mu1 minus 5. Means if you take the mean for all men and subtract 5, the mean for all men who use the drug will be less than that. So we're saying that it's less than 5 below, more than 5 below. So what that means, right, I'm claiming that mu2 is below mu1 minus 5, which is the same thing as mu1 minus 5 is greater than mu2. And so now I have to swing this over here, subtract mu2 from both sides, add 5 to both sides, and I get a claim that says mu1 minus mu2 is greater than 5. And that should make sense. Right? I'm saying that when you take the no drug group and subtract the mean from the drug group, that difference will be greater than 5. I mean, it's 30 here. Hopefully we can transcend to the population and at least get 5. So let's see. So the claim looks very much the same, only instead of having a 0 here, I have a 5. Right? So the claim is that the difference in population means is greater than 5. The null gets the equal to sign, and the alternate gets the claim. Now we need to calculate the test statistic. The degrees of freedom stays the same, and in fact the A and B, everything stays the same. Right? Until you get down here to the test statistic. Right? Now this delta is not 0, it's a 5. So we take the difference in sample means and subtract 5 and then divide by the square root of this sum. You get 2.086. So that's the test statistic, right? Test statistic. So I need to take that test statistic and determine whether or not I reject the null hypothesis. If we use the critical value method for us table users, we need to put 0.05, that's the significance level, one tail with 18 degrees of freedom. And we actually did that, but we'll take a look at it again. So it is one tail. So I'm in this row. 0.05 is the significance level. I still have 18 degrees of freedom, but now I'm in this second to last column. So my critical value is 1.734. So let's go back to our problem here. Critical value is 1.734. And again, I didn't draw the distribution, but if I did, it looks something like this, right? On the right, I would have 1.734, and everything to the right of that would be in the rejection region. My test statistic, 2.086, is in the rejection region, right? My test statistic is over here, so that's good. I get to reject the null hypothesis. If you have software, the p-value comes out to be about 0.0257. And that's smaller than alpha, which is 0.05. So again, by the p-value method, we reject the null hypothesis as well. So that's good. We get to support our claim. At the 0.05 significance level, the sample data supports the claim that the mean cholesterol level for all men who use the drug is more than 5 milligrams per deciliter below the mean for those who do not use the drug. So it's a stronger statement. It's not as strong as we were able to make when the data was paired, but it's still better than just saying it lowers it. At least in this case we say it lowers it by more than 5. So that sounds a little better. But now, suppose we want to go for more than 5. Suppose we want to go for 10, right? Can you support the claim that the mean cholesterol level for men who use the drug is more than 10 milligrams per deciliter below the mean for those who do not use the drug? Use a 0.05 significance level. So we have the same significance level, same data. The only thing is my presumed difference in the null hypothesis is no longer 5, it's 10. And what that does is it changes our test statistic to 1.700. And what we see, and we're going to have the same critical value, 1.700 is no longer in the rejection region. Right? So we would fail to reject the null hypothesis. Right? And if we fail to reject the null hypothesis, we can't support our claim. So, at the 0.05 significance level, there is not enough sample data to support the claim that the mean cholesterol level for men who use the drug is more than 10 milligrams per deciliter below the mean for those who do not use the drug. Right? So, we were able to get 5, but not quite 10. And it shows you that supporting a claim with independent data is a little harder, because when that data was paired, we were able to get 20 at the 0.05 significance level. Right. Now that's because there's more variation when the samples are independent. Okay. So we were only able to get 5. When you look at the actual difference in means, it's over 30 in the sample, but we can't even get over 10 in the population. All right. So we're going to do one more type of problem along these lines, and it's a little terminology that I'd like to introduce that is a simplified case. In this case, suppose we want to run a significance test or a hypothesis test, but we have population data. Right? Because sometimes we actually have the population data. And let's take a look at this example, and then we'll go back to that previous paragraph. Joe plays basketball for the Wildcats, missed some of the season due to an injury. He did some calculations that showed the mean number of points scored by his team was greater when he played. Right? So basically, with Joe, the mean was 74.1 points scored, and without Joe, the mean was 65.7. So clearly, based on the games played, the mean score was higher, right? But we want to ask ourselves, was it significantly higher? You know, is that 74.1 significantly higher than the 65.7? And the problem is we don't really have a sample. We have all the games. We have all 20 games that were played that season, so there's no real sample. But what we do is we sort of treat it like a sample, and that sample is from all the games that could have been played, right? So what we're doing, we're going to call this a test of significance, in that we're testing on population data whether or not this 74.1 is significantly greater than 65.7. Right? Is it significantly greater? Right? And so that's what I'm going to call a significance test. Actually, the difference between a significance test and a hypothesis test is actually more subtle than that. But we will call such a test a significance test. So we have population data, and we want to determine whether there is a significant difference or whether that difference may just be due to random variation. Right? There are also some small phrasing differences that we'll get to as we demonstrate some examples. Okay, so here we go to the example. Joe plays basketball. And let me emphasize this. So this is a significance test. We've been doing hypothesis tests. The only difference is that we actually have population data, but treat it like sample data. So what we do is we take this population data and treat it like a sample. Treat it like a sample. And then do a hypothesis test. So we're not doing anything different. It's just a matter of what we are calling a sample, right? This is all of the games played, but we're treating it as a sample of all of the games that could have been played, right? Okay, so here we have Joe, plays for the Wildcats, missed some of the season. He did some calculations that showed the mean points scored when he was playing was greater than the mean points scored when he wasn't. And here we test whether or not the mean was significantly greater. Is that difference significant? Right? And a significant difference is one that is unlikely to be a result of random variation. That's what we mean by significant. Okay. So, we have our table of data, and they're population means, but we treat them like sample means. The degrees of freedom is given. I told you I'd give you this down here, 16. And we're going to test this claim. Test the claim that the mean points scored by the team was significantly greater when Joe played. Right? So when we say significantly greater, we mean that it probably was not due to random variation. There was something significant going on. Okay, so we're going to treat it like a sample, and the claim is that the mean for all the games when Joe played here is greater than the mean for all the games that Joe did not play. All right? And so, subtracting mu2 from both sides, we get mu1 minus mu2 is greater than 0. So we have a right-tailed test. So that's our claim. Mu1 minus mu2 is greater than 0. The null hypothesis gets the equality, and the alternate supports the claim. Then we calculate the test statistic, and everything you really need is right here. Sample mean for games with Joe, sample mean for games without Joe. Delta comes from the null hypothesis. That is a 0. The variance is given right here. The variance for sample 1 is 42.5 divided by N1, which is, there's 12 games where he played. The sample variance for sample 2 is 38.2, and the size of sample 2 is 8. And when you plug all these in and do it carefully in your calculator or with software, you get a test statistic of 2.913. So now we have to determine, do we reject or fail to reject the null hypothesis? Again, we're going to go with the critical value method. This is a 0.05 significance level. One tail, so right tail, 16 degrees of freedom, right? I gave you that here. Okay, so 0.05, one tail, 16 degrees of freedom. Go back up here. So again, I'm 0.05. So again, I'm one tail, 0.05. So I'm in this second to last column. 16 degrees of freedom. So at the intersection of this row and this column is 1.746. Right, so we take 1.746 back to the problem. 1.746. And again, I didn't draw the distribution, but if I did, look, the t-distribution looks like a normal curve, so when I draw it, they look exactly the same. Both of them are done pretty sloppily when I do it by hand. So the critical value is 1.746. The rejection region is everything to the right. This is a right-tailed test. And my test statistic, 2.93, is certainly in the rejection region. All right, test statistic is in the rejection region. We reject H0. If you have software, you can calculate the p-value, and it turns out to be 0.0051, which is certainly smaller than alpha, which in this case is 0.05, the significance level. Conclusion. So here's how the phrasing goes. The data supports the claim that the mean points scored by the team was significantly greater when Joe played. Right? There's not really a hypothesis test going on, right? We know that the mean when Joe played was greater, but we're testing whether or not it was significantly greater. And by treating it as sample data, if we can reject the null and support the claim, then we have a significant difference. What that means, this means it is unlikely that the increase, that increase in points, was due to random variation. Right? But there was something significant going on. And the p-value p-value actually tells us how unlikely it is. It tells us really how significant something is. The smaller the p-value, the more significant a difference is, right? So in this case, our p-value is 0.0051, so it's 0.5% about. So what that means is we would expect an increase of this magnitude, that difference, to occur about 0.5% of the time just by chance. So it is possible that this difference in mean scores was due to chance. It's just not very likely, right? Because it's not going to happen that often. So that's our significance test on population data. And again, that's a phrase that I use in this book, but is not necessarily generally agreed upon, right? So in this book I call it a significance test because there is no real hypothesis being tested. We're looking for a significant difference. All right, and that wraps up chapter 9.2, right? So we have one more section in this chapter, and then we'll do the summary worksheet. So I will see you in chapter 9.3. Bye.